1 half e to the t minus 2. Hey there. This is for AP Calculus AB. This is content from 1.4 where we talk about integration formulas and ultimately the net change theorem, some ideas of what you can do with integration in a contextual situation. This is checkpoint 1.22 where we're going to find the net displacement and total distance. They're very similar ideas and yet dramatically different when we calculate. Well, dramatically is a strong word. And this is traveled in meters given a velocity function f of t equals 1 half e to the t minus 2 over the interval of 2 seconds, 0 to 2. By the way, net displacement actually means something along the lines of this one. If you, this is going to get dark, sorry. If you die in the same hospital where you're born, your net displacement for life is 0. So you might have traveled a total distance of around the world 100 times. Or, you know, and again, this is all relative to Earth position. But the idea being, you know, no matter how far away you go, when you come back home, your displacement, your net displacement from where you originated is returning back to 0. So when we evaluate an integral, we're taking into consideration some change or some area, some movement to the one side that is canceled out by further movement to the other side. And overall, net will be the amount of what's left after you calculate those things. Some great pictures, or at least some ideas earlier on in the text. Check them out. To find the net displacement, we're just going to evaluate the integral. So you see that we have here f of t, 1 half e to the t minus 2. So let's go and integrate 1 half e to the t minus 2 from 0 to 2 of, don't forget, your dt. You'll lose points if you don't have that on there. All right, if I go to Desmos and evaluate it directly, like that's fine, but I want to continue trying to use fundamental theorem of calculus just to kind of make sure that FTC part 2 is getting lodged in your brain. 1 half e to the t, well the 1 half can pop out from 0 to 2 of e to the t dt, and then minus 2 integral of nothing dt, but it's technically of a 1, so that's our inside, our integrand. If we don't write it down, the integrand is still, you know, a constant number 1. Now, integrate. So, turns out if the derivative of e to the t is e to the t, then the integral of e to the t is e to the t. So, we're not going to see any change here. We're going to have 1 half e to the t from 0 to 2 minus 2 integral t, right? The integral of 1 is t, 0 to 2. Now evaluate. So evaluate, and we're going to get 1 half e squared. E to the 0 is 1, so minus 1 half. And then over here, minus 2 t squared, which is, not t squared, it's 2, minus 2 times 2. You see my brain broke for a minute. Okay. So there we go. We have it. The minus 0, if I really want to be picky. There's 1, 2, 3, all 4 parts for 1, 2, 3, 4 evaluations. And then 1 half e squared, I guess that'd be 4 and a half, 9 halves, minus 9 halves. There we go. That's our formula. E to the, oh, there's some really fun things we could do with that. Not the point of this video. This is net displacement. Now, the issue that we have to further recognize with this problem is that when we look at the total distance, this says, yeah, some of that distance is negative, some of that distance is positive. Cool. But what about just saying, well, you got to spend the gas money to travel that direction and then spend the gas money to travel back the other direction? Direction doesn't matter. You're still spending money to travel a distance. So we're going to look at the positive elements of this list. And I graphed this for you. I graphed it in Desmos. Here we have in Desmos the function exactly as it's written. F of t equals 1 half e to the t minus 2. But if we go ahead and we use absolute value of f of t, check. That didn't work. Let's go x. There we go. Little pro tip with Desmos, it doesn't really like graphing things with different letters. It likes graphing with x, and so that's what I did. Now imagine, mind you, we're only considering if the function is going in positive distance amounts, right? So really I'm just saying let's make the function have all of its positives. That's it. we're also going from 0 to 2. So I might as well set those limits of integration here as well. 0 is less than or equal to x is less than or equal to 2. And 0 is less than or equal to x is less than or equal to 2. Okay? And I guess I'm still having some problems, so I'm going to change all of my t's. Oh no, I chose an x right there. I'm going to see if I can continue to use what's here. Perfect! There it is. So we're not really considering the red function for total distance. We're considering the blue function. And if you notice, this blue function here has a section where it touches the x-axis. We need to know where that is. In other words, what we need to know for total distance, let's see if I can capture this on the document camera. We need to know where 1/2 e to the t minus 2 equals 0. We need to solve for t in this problem. So I'm going to add 2 to both sides. 1/2 e to the t equals 2. Multiply by 2 to both sides. E to the t equals 4. Now we got to get t by itself. And remember that we have t, which is an exponent. That means we got to use logarithms. Natural log will move the t out front. ln of 4. So t equals the natural log of 4. Yeah, we should probably actually evaluate that. But I'm willing to bet it's pretty much 1.386. And it's 1.3863 if you want to be more accurate. More precise? More precise. So which should you use? Well, here's what we're going to do. We're going to take all of the work that we did up here for net displacement, and we're going to split the function into the two places where it's actually, well, this part it's negative and this part's positive. Let's go back to the original function. For the section where the graph is negative, we want to calculate that area, but we're going to get a negative area. So you'll see me use a minus sign. I want to use the concept of a negative to flip that area back around. Here we go. I've got the integral. Okay, this negative area stops being negative at natural log of 4. So I'm going to integrate from the natural log of 4, well, from 0 to the natural log of 4 of our function. 1/2 e to the t minus 2 dt. Now, this is continuing to show you what I'm talking about. The issue is this is going to result in a negative. Let's try that. Watch. Here we go. We'll use Desmos to prove the point. Integral from 0 to the natural log of 4. I want to use natural log of 4. It's actually shorter than writing out all of those decimals, 1.38629436112. You should write all of them down, but we have an expression that's shorter. Let's do of f of t dt. Notice how it's negative? Make it positive. I want to show that right here. Watch. Make it positive. Because a negative and a negative makes a positive. And we're going to add to that the integral from natural log of 4 to 2. All of everything from that point on is going to be positive. So here it is, 1/2 e to the t minus 2 dt. I'm going to assume that you're good with this part right here. Oh no, I can actually just jump to that. This will be easy. So equals, I'm bringing in the notes from the previous section, and I'm messing with settings on my computer. There we go. 1/2 e to the t minus 2t. Yeah, let's leave it alone. From 0 to the natural log of 4. This is going to be negative minus 2t from 0 to the natural log of 4 plus, we got to add to that the other one. So here's the same thing. I'm going to kind of run out of some space. I'm going to try to write right here. 1/2 e to the t from the natural log of 4 to 2 minus 2 of t from the natural log of 4 to 2. And all of this. These are added together. That's this integral written out with fundamental theorem here, and this integral written out with fundamental theorem here. I don't want to calculate this by hand because we already did, and I'm running out of time. This video is already approaching 10 minutes. So let's go. We have the negative of this, and we're going to add to it plus the integral from natural log of 4 to 2 of f of t dt. We get a positive value of 1.73 well, 97. Let's not write it that way. Let's go 1.740. And this was referencing what units? Meters. There you have it. Total displacement versus net displacement. Thanks for watching this video.